Hi, this is our last video, or our last section for Chapter 9. It's about now significance tests for population means. We just had finished up doing population proportions. So again, we're going to go through our conditions. So same as before, conditions. We're going to perform the significance test. We're going to talk about a confidence interval and how it relates to significance tests. And then we're going to talk about what does it mean if we're using paired data. So those are our objectives of this video. Again, when we did confidence intervals and significance tests for proportions, they were based on z values. Now that we're moving into means, again, mu, we're going to be using that t distribution again, so that other table. And we have to know our degrees of freedom. And then it says, except in that rare case when the population standard deviation is known, then we can go back to the z table or use that infinity line. So everything that we learned in section 8.3 on how to construct confidence intervals, we're going to look at those details about mu and use them to construct significance tests. So that's what we're doing here, carrying out a significance test for mu. So I'm just going to start with an example. We had, in your book, there was an early example. A company claimed to have developed new AAA batteries that last longer than regular AAA batteries. Based on years of experience, the company knows that the regular AAA batteries last for 30 hours of continuous use on average. They decide to take a simple random sample of 15 new batteries, and they lasted an average of 33.9 hours with a standard deviation of 9.8. Do these data give convincing evidence that the new batteries last longer on average? So they're going to again ask you about convincing evidence because we're doing a significance test. So whenever you do a significance test, your first step is to state your hypotheses. So when we do that, our null, again, is mu equals 30 hours. We think the AAA batteries last 30 hours. And our alternative is that they claim that the new batteries, their average is greater than 30 hours. And again, this is what it means to describe or define your parameter. Mu equals the true mean lifetime or true mean hours of the new deluxe AAA batteries. So you have to always state your hypotheses if they're asking you for convincing evidence. And then the next thing that we did is we have to check our conditions. Remember, our conditions are, should it be random, well-designed random sample or randomized experiment? We have that 10% condition. When sampling without replacement, check that and they again write it this way, the sample size is 1/10 of the population. You could also write it as the population is 10 times the sample size. And then the last condition is that normal or large counts condition or large sample. And because again we're dealing with means, this one changes a little bit. If the population has a normal distribution, we're good. If the sample size is larger than, say, 30, we're good to proceed. If the population distribution, though, shape is unknown and your sample size is less than 30, this is where we had to make those graphs like we did earlier. You can make a histogram, you can make a box plot, you can make a normal probability plot. And then that last line, do not use that T procedures if there's strong skewness or outliers. Again, strong skewness would be there's a slight gap, and maybe that point is not an outlier, but it has to be really strongly skewed, very stretch out or spread out. So we did our hypotheses, now you did your conditions, and now we're going to actually do the test. And it looks very similar to when we were doing proportions. Again, there's a test statistic, and that equals the statistic, in this case, what was the average of your sample or mean of your sample. The parameter, again, as it states above, is what came out of our hypothesis, and then the standard deviation of our statistic. Again, when we're testing our null, ideally it would be, do we actually know the population standard deviation? And we would divide that by the square root of n, the size of our sample. However, we know that that's really kind of unrealistic. So again, notice the denominator is that standard deviation of the statistic. They replace sigma with an s again, divided by the square root of n. X bar is the sample mean, and then mu is the mean that came from our hypothesis. And then just kind of reminding ourselves that we're calculating a t, and t is going to have a degree of freedom of n minus 1. So this is the main formula that we're going to be using in section 9.3. So if you want to write that down, that would be a good one to write down. Okay, so let's actually do the test for our battery example. Again, the battery company wanted to have our null be the batteries last 30 hours versus they're greater than 30 hours. And we're basing this test on our 15 new AAA batteries. And they had, again, a mean lifetime of 33.9 and a standard deviation of 9.8. Sometimes they'll give you that data. Sometimes, like we saw last chapter, you'll have to calculate it using a table. So the first thing is to, again, use our formula. Here's that formula I told you to write down. Plug in your values, 33.9 minus 30, standard deviation divided by the square root of n, and we get our test statistic t. Okay, so we need to figure out, again, a p-value. That was sort of our last step, was a p-value. The p-value is the probability of getting a result this large, the 33.9, or larger in the direction of, so that's why they say larger, of your hypothesis. So how do we find that p-value? First, we have to go to the t-table, and we're going to the row for degrees of freedom 14, because we had 15 our sample, n minus 1 is 14. Then, since the test statistic falls between values 1.345 and 1.761, again, it's going to give you the upper tail always. So the upper probability is between 10 and 5%. So when you're looking in the table, it's always going to kind of give it to you backwards, but that means our p-value is between 5 and 10%. So if you pull out your table, again, we're looking at the T one. We're going to the degree of freedom of 14 row, and you're looking straight across, and you're looking for the values in which 1.54 fits between. So that's why they had two sort of T numbers that they talked about, because it's looking for 1.54 is between those. And then when you look straight up, that's how they had 5% to 10% for our p-value. So our p-value for this test is between 5 and 10%. The last thing that you would do in this particular problem would be then to interpret your results. Is there evidence or not? And because you have a p-value that's between 5 and 10%, if you said that your significance level, your alpha value was 5%, then you would say, no, I have to fail to reject the null because my p-value is larger than 5%. How much larger? I don't know. It just falls somewhere in that range. If you picked a significance level of 10%, you could say that we have evidence, and we would reject the null because the p-value is less than that alpha level. So again, stating that alpha level at the very beginning is important because that will allow you to draw your conclusions. So just kind of some hints kind of along the way, or things to watch out for. Again, table B will always give us a range of p-values this time. It's not going to give you a particular percentage like the Z table does. Sometimes table B includes probabilities, again, 1 through 30, and then 40, 50, 60, 80, 100, and 1,000. So we're always going to sort of round down or go to that lower level like we did before. And then, again, table B shows the probabilities only for the positive T's. So even if you calculate your T and you get a negative, we know that that table is symmetric so that you know that the numbers are going to be exactly the same. So just kind of things to be aware of. Again, one last time, what are we doing? We're doing a one sample T test. This is the formula that we were just mentioning. Again, you could have one tail on the upper end, one tail on the lower end, or you could have two tails. Again, two tails just means you're not sure if it's equal, greater than or less than, you just write it's not equal to. So again, just talking about two-tailed tests and confidence intervals and how that's starting to relate. So the connection between two-sided tests and confidence intervals is even stronger for means than it was for proportions. That's because both inference methods use means and use the same standard error for the sample mean in the calculations. So you notice that they're have all of the same parts to them. So again, a two-sided test at a significance level of, we'll say, 5%, and that means that the confidence interval is 95%, 1 minus alpha. Oops, gives similar information. So again, we can have evidence in both cases now, and we kind of did that in our last chapter where we said, oh, it's not in our interval, so therefore we can't agree with the claim. You would have the same thing. You'd have that ability to reject the null because it's not part of your claim. And that's kind of what they're saying with these second two bullet points. And we'll go over that in a few examples together. The last thing that it said we were going to do is quickly talk about paired data. Paired data is when you're doing sort of comparative studies and you're looking at convincing sort of a single sample investigations. Studies that involve making two observations on the same individual or one observation on two similar individuals are considered paired data. We referred to this as like a matched pairs experiment earlier in the year, but now we call it paired data because it's, again, same individual, two observations, or one observation, very similar individuals. Again, we're just comparing between those two quantitative values, and we're doing the same conditions, but we're doing them only if the one sample t procedures work for the mean difference. So you always want to be comparing the difference part as we go through. Again, they're often called as paired t procedures, paired data, matched pairs. All of those words are sort of interchangeable as we keep moving forward. The last part is just kind of, again, a few key things not to forget about. Carrying out significance tests is pretty simple, especially when we're going to use our calculator later, but using them wisely can be kind of muddy. So again, how large of a sample do you need? If you want a smaller significance level, it requires stronger evidence to reject the null. So that just means you want a larger sample to make it kind of more evidence. Again, high power gives a better chance of detecting a difference when it really exists. And at any significance level and desired power, detecting a small difference between the null and the alternative requires very large samples. So these are just things to be aware of as we kind of continue going through. Other things that you should be aware of is there is a difference between statistically significant and practically important. So you could find evidence that something is different or that we reject the null, but it might not have any real-world practical importance. So even tiny differences or large differences could be not even practically important. Likewise, very small differences in the null might show significance but mean nothing in real life. The last thing that you should kind of be aware of is statistical significance ought to mean that you have found a difference in what you're looking for. And then again, the reason behind this is you decided what you were looking for first. So you have to know where you're going with your test in order to find evidence for it. You can't kind of, like in the court of law, you're trying someone for one particular crime. Even if you think you have evidence that this person committed another crime, that's not what they're on trial for. So you can't draw any conclusions about that. So if you're trying them for murder of this female individual and you find out through your questioning that he probably murdered some male, that doesn't matter. That's what you weren't looking for evidence of that. So again, just be aware that if whatever you're searching for evidence for, that's all you can kind of decide on. So that kind of wraps up 9.3. These are the things that we went over, and now you should be able to complete some of the questions from section 9.3 on the worksheet or in your homework. If you have any questions, feel free to stop by during resource, and we can go over any of this again. Thanks.